Hi, I'm Alex. This is Oh, That's Why, a podcast about JavaScript, finally making sense. Let's dig in. Welcome to Season 2. Season 1 was about how JavaScript runs, the engine, the memory, the execution model. This season is about something you interact with every single line of code, the data itself. How JavaScript stores it, reads it, compares it, and converts it. And we are starting with the question I get asked more than almost any other. You pass an object into a function. The function changes one property. You never returned anything. You never reassigned the original variable. You come back to check the original, and it changed. How? If the answer you have been given is because objects are passed by reference, that is correct, but it is not enough. Because the next question, which always follows, is why? Why are objects passed by reference? Why are numbers not? Who decided this, and what were they thinking? There is a clean, logical answer. And once you have it, this entire category of surprising behavior stops being surprising. Two scenarios. Both involve giving someone information. In the first scenario, you write something on a post-it note and hand it to them. A number, a name, a yes or no. They now have their own copy of that information. You could tear up your original post-it and it would not matter. Their copy is independent. Whatever they write on their version has no effect on yours. In the second scenario, instead of writing the information down, you give them your home address. Now you are not handing them the contents of your house. You are giving them the directions to find it. They can go there. They can rearrange the furniture. They can change things. And when you get home, everything they changed is changed, because you both have directions to the same place. There is only one house. That is the difference between primitives and reference types in JavaScript. A primitive is the post-it. A number, a string, a boolean, null, undefined, a symbol, a big int, these are values. When you assign a primitive to a variable, the variable holds the actual value. When you copy it to another variable, you copy the value. Two separate post-its, independent. A reference type is the address. Objects, arrays, functions, these live somewhere in memory. When you assign an object to a variable, the variable holds the directions to find it, not the object itself. When you copy that variable to another, you copy the address. Now, two variables point to the same house, and anything either of them does to the furniture affects the one shared place. That is why passing an object to a function and modifying it inside changes the original. You passed the address. The function went to the house and rearranged something. Your variable still points to the same house. It comes back changed. Let's go deeper. JavaScript has 7 primitive types: string, number, big int, boolean, undefined, null, and symbol. The post-its. They are immutable. You cannot change a string by modifying individual characters. You can only replace the whole thing. They are stored directly in the variable. When you compare two primitives, JavaScript compares the actual values. When you copy them, you copy the values. Simple, predictable, independent. Everything else is a reference type. Objects, arrays, functions. The houses. They exist at a location in memory. Variables that hold them are holding directions, not contents. Now, const. This is where people get tangled. You declare a variable with const and assign it an object. You try to reassign the variable to a different object, and you get an error. Const is protecting the address. You cannot change which house your variable points to. But then you modify a property on the object, and it works fine, because const is protecting the directions, not the house. The property change goes through the directions, modifies the house, and comes back. The directions themselves never changed. Const is satisfied. This is not a loophole. It is the expected behavior once you understand what const is actually protecting. Now, copying. If you want a genuinely independent copy of an object, a separate house, not a second set of directions to the same one, you have to be explicit about it. A shallow copy duplicates the top-level properties. Spread syntax does this. The new object is a different object, a new address. But if any of the properties are themselves objects, those inner objects are still shared. You have a new house, but the furniture in it is still pointing to the same places as the original. Change a nested property through either copy and you affect both. A deep copy duplicates everything, the object and all objects it contains, recursively. Every level gets its own independent copy. No sharing anywhere. This is more expensive, and it is not always what you need. But when you genuinely need full independence, it is the only option. The choice between shallow and deep copy is not about style. It is about whether your data has nested objects and whether you need those to be independent too. The accidental mutation trap is the one this whole episode has been leading to. You pass an object to a function expecting it to do its work without affecting the original. The function modifies a property. The original changes. You are confused because you did not ask for that. The fix depends on what you actually need. If the function should read the object but not modify it, rely on discipline and document that intent. If you genuinely need the function to work on a copy, pass it a copy. Spread for shallow objects. A proper deep copy for nested ones. Array mutations are the second trap, and this one is sneaky because it hides in plain sight. Arrays are objects in JavaScript. Every method that modifies in place, push, pop, shift, splice, is modifying the original. Every method that returns a new array, map, filter, slice, concat, leaves the original untouched. These two groups are easy to confuse. The symptoms look exactly like the object mutation bug, and the fix is just knowing which method you're calling. Knowing which mutate and which don't is worth the time it takes to learn them. The third trap is equality. Two objects that appear identical, same keys, same values, are not equal. The comparison checks whether the references point to the same object, not whether the contents match. This bites hardest in React. You create a new object with the same contents. React sees a different reference and renders unnecessarily. Understanding reference equality is the beginning of understanding how to write efficient React components. A primitive is a value. An object is a location. When you copy a primitive, you copy the value. When you copy an object, you copy the directions to find it. Season 2 is about data, and this is the foundation. Every question about how JavaScript stores things, compares things, and converts things traces back to whether you are working with a value or a location. We will be using this distinction for the rest of the season. The companion article on Medium covers shallow versus deep copy in detail, with examples of when each is appropriate. Link is in the show notes. Next week, type coercion. Why JavaScript accepts adding a number to a string. Why the result often surprises you. And why understanding the rules means it never has to again. I'm Alex Vega. This is Oh That's Why, Season 2. One concept at a time. See you next week.